Nenomatica, where mathematics meets YouTube excellence. Welcome! In this short guided video, we will solve a nested radical equation step by step following a clear, rule-based structure with visual tip boxes. First, we display the example and the problem statement. Step 1. Use the rule. If the square root of a equals b, then a equals b squared. We square both sides to remove the outer square root. This gives 15 plus the inner square root equals 25. Step 2. Isolate the remaining square root by subtracting 15 from both sides. Then compute the difference 25 minus 15. The inner root equals 10. Step 3. Apply the square both sides rule again to remove the inner root. Squaring 10 gives 100. So 2x plus 80 equals 100. Step 4. Solve the resulting linear equation. Subtract 80 from both sides, then divide by 2. We get x equals 10. Step 5. Always check for extraneous roots in radical equations. Substitute x equals 10 back into the original expression. The left side simplifies to 5, matching the right side, so x equals 10 is valid. Final result. The solution is x equals 10. Enjoy a quick celebration. Summary. We squared both sides twice to remove the radicals, solved the resulting linear equation, and verified the solution to avoid extraneous roots. Practice similar problems to master the process. Example. We will follow the exact step order shown in the reference and solve the radical equation. Our problem is x equals square root of x plus 6. Then we will verify candidate roots to avoid extraneous solutions. Step 1. Square both sides of the equation. This is valid because if it equals b, then a squared equals b squared. Be careful, squaring may introduce an extraneous root, so we will check solutions at the end. Step 2. Simplify the right side, because the square of a square root returns the inside. So we get x squared equals x plus 6. Step 3. Rearrange to standard quadratic form ax squared plus bx plus c equals 0. Move everything to the left side to obtain x squared minus x minus 6 equals 0. Step 4. Factor the quadratic. We look for numbers whose product is negative 6 and sum is negative 1. Those numbers are negative 3, 6, and sum is negative 1. Those numbers are negative 3 and positive 2. So the factorization is left parenthesis x minus 3, right parenthesis left parenthesis x plus 2, right parenthesis equals 0. Set each factor equal to 0 to get candidate solutions x equals 3 and x equals negative 2. Step 5. Check both candidates in the original radical equation to avoid extraneous solutions created by squaring. First substitute x equals 3. 3 equals the square root of 9, which is 3. That works. Next substitute x equals negative 2. Negative 2 equals the square root of 4, which is 2. This does not work because negative 2 is not equal to positive 2. Therefore, the only valid solution is x equals 3. Final answer x equals 3, in green. Great job, following the exact structure and step order. Summary. We squared both sides. Great job, following the exact structure and step order. Summary. We squared both sides, simplified, rearranged to standard form, factored, solved, and finally verified to reject the extraneous root. Remember to always check radical equations after squaring. Now, the problem statement in bold, orange. Isolate the square root term. We move y to the right side to leave the square root by itself. Step 1. Isolate the square root term. We get square root of y minus 4 equals 4 minus y. Square both sides to eliminate the square root. Step 2. Square both sides. We obtain y minus 4 equals the quantity 4 minus y squared. Expand the squared binomial. Step 3. Expand the right side using a minus b quantity squared equals a squared minus 2ab plus b squared. It becomes y minus 4 equals 16 minus 8, y plus y squared. Rearrange to form a quadratic equation. Step 4. Bring all terms to the right side and set the equation to 0. We obtain y squared minus 9, y plus 20 equals 0. Factor the quadratic equation. Step 5. Factor to get the product of two linear terms. we have left parenthesis y minus 5 right parenthesis times left parenthesis y minus 4 right parenthesis equals 0, leading to y equals 5, or y equals 4. Verify by substitution. Step 6. Check y equals 4. Substituting gives 4 plus the square root of 4 minus 4 equals 4, which is valid. Step 7. Check y equals 5. We get 5 plus the square root of 5 minus 4 equals 6, which does not equal 4, so it is not valid. Our only valid solution is y equals 4. In this guided example, we solve a radical equation step by step, following the exact structure shown in the source solution. Here is the example. Below it, we display the problem statement in bold orange latex. Step 1. Square both sides. This mirrors the written solution, where the next line is open parenthesis square root, y close parenthesis squared equals open parenthesis, y minus 2 close parenthesis squared. Step 2. Expand the binomial and simplify. The right-hand side becomes y squared minus 4, y plus 4. So we write y equals that expression. Step 3. Move all terms to one side to set the quadratic equal to 0, yielding y squared minus 5, y plus 4 equals 0. Step 4. Factor the quadratic. We get open parenthesis, y minus 1 close parenthesis times open parenthesis, y minus 4 close parenthesis equals 0. Step 5. Apply the zero product property. Either y minus 1 equals 0 or y minus 4 equals 0, which gives the candidates y equals 1 and y equals 4. Step 6. Check for extraneous roots in the original equation. Substitute y equals 1 into square root y minus y equals negative 2. That gives 0, which is not negative 2, so y equals 1 is extraneous. Substitute y equals 4, and we get 2 minus 4 equals negative 2, which works. Therefore, the solution set is the single value 4. We will solve two radical equations by following a precise step-by-step algorithm. Our focus is on understanding why some radical equations have no real solution. First, we display the word example. Then we state the first problem. Rule box. Solving radical equations reminds us to isolate the radical first. We show the rule. Step 1. Analyze the equation. We isolate the radical by subtracting 3 from both sides. Show the isolate rule. Write the isolated radical equation. Key property. A principal square root is never negative. Show the domain rule box. Conclude there is a contradiction because the right side is negative. We finalize the solution set in standard set notation. Display the empty set conclusion. Quick challenge prompt for the learner. Now, we consider a second equation with two radicals. We again display the word example and state the new problem in orange. We isolate the sum of the radicals. Show isolate rule. Write the isolated equation. Apply the non-negativity property to a sum of square roots. Show the rule for sums of non-negative numbers. Conclude again that there is no real solution. Finalize the solution set for the second equation. Display the empty set. We finish with a brief summary. Quick challenge. Can you predict the first algebraic move before it appears? Rule. Square both sides of an equation. Then we apply it to both sides to remove the radicals. Rule. The square of a square root equals the radicand. Simplify each side carefully. Now solve the resulting linear equation by collecting like terms. Always verify. Substitute x equals 4 into the original equation and compare both sides. Both sides equal 4, so the solution is valid. Present the final answer in green. Quick recap. Square both sides, simplify radicals, solve the linear equation, and verify the candidate solution. Here is a compact summary. Take a moment to review, and then try a similar practice problem on your own. We will solve a radical equation step by step, exactly following a clear algorithm, and verify every candidate solution. First, here is the example and the problem statement. Rule 1. Square both sides to remove the radicals you see immediately. Step 1. Square both sides to eliminate the square roots. First, write the squared form. Then expand the right side using the binomial pattern. Now, isolate the radical term. We subtract 9 and the quantity 3p plus 2 from both sides. Then simplify to a clean linear multiple of the radical. Divide both sides by 2 to simplify the coefficients. The result is 3 times the square root of 3p plus 2 equals negative 4 minus 3p. Square both sides again to remove the remaining radical. After squaring, square both sides again to remove the remaining radical. After squaring, expand the right-hand square completely. Now expand and simplify to obtain a standard quadratic equation. Bring all terms to one side and combine like terms. Solve the quadratic using the quadratic formula. Compute the discriminant, then simplify to the two candidate values for p. Radical equations often produce extraneous solutions. Check both candidates in the original equation. For p equals 2/3, compute both sides. Then, for p equals negative 1/3. Since neither candidate satisfies the original equation, there are no real solutions. Summary: we squared both sides twice, isolated the radical cleanly, simplified to a quadratic equation, solved using the quadratic formula, and checked both candidates, concluding that the equation has no real solutions. Example: we will solve a radical equation step by step, following a clear algorithm. Problem: solve the equation open parenthesis 1 minus square root of x close parenthesis over open parenthesis 1 plus square root of x close parenthesis equals 1 minus x. Step 1. Eliminate the denominator by multiplying both sides by 1 plus square root of x. Step 2. Expand the right-hand side using the distributive property. Step 3. Collect terms with square root of x on one side. After simplifying, we get x times square root of x minus 2 square root of x equals negative x. Step 4. Factor out square root of x. Step 5. Square both sides to remove the square root. Step 6. Simplify using the power of a product and the square of a negative. Step 7. Move all terms to one side to set the equation to 0. Step 8. Factor out x. Step 9. Expand the square of a binomial and simplify inside the bracket. Step 10. Combine like terms. Step 11. Factor the quadratic inside the bracket. Step 12. Apply the zero product property to get the candidate solutions. Step 13. Check each candidate in the original equation to discard extraneous roots. Final answer: the valid solutions are x equals 0 and x equals 1. Summary: here is the label and the problem statement. Square both sides to eliminate the outer square roots. We apply the rule: if a equals b and b are non-negative, then a squared equals b squared. So the quantity 2 plus square root of 1 plus x, all squared, equals the square root of x squared. Expand the left-hand side using the binomial square identity. The square of a plus b equals a squared plus 2ab plus b squared. Expanding gives 4 plus 4 times the square root of 1 plus x plus 1 plus x equals x. Collect like terms. We transpose x from the right to the left and combine constants. That simplifies to 5 plus 4 times the square root of 1 plus x equals 0. Isolate the radical term. Subtract 5 from both sides. We obtain 4 times the square root of 1 plus x equals negative 5. Interpret the result. A square root is always non-negative, so the left side is at least 0, but the right side is negative. Therefore, there is no real number x that satisfies the original equation. Example: we will solve the radical equation 1 equals t plus the square root of 2t minus 3, following a strict step-by-step algorithm, and check for extraneous solutions at the end. Step 1. Isolate the square root term. Use transposition. Subtract t from both sides to get 1 minus t equals the square root of 2t minus 3. Quick challenge: which part changed from the previous line? Step 2. Square both sides. If x equals y, then x squared equals y squared. We square the left and the right. Step 3. Expand and simplify. Use the binomial square identity. Expanding gives 1 minus 2t plus t squared equals 2t minus 3. Step 4. Collect like terms on one side. Move terms to obtain a standard quadratic. We get t squared minus 4t plus 4 equals 0. Step 5. Factor the quadratic. Recognize a perfect square trinomial. That gives open parenthesis t minus 2 close parenthesis squared equals 0. So the candidate solution is t equals 2. Step 6. Check the candidate in the original equation to avoid extraneous solutions. We plug t equals 2 back into 1 equals t plus the square root of 2t minus 3. 1 equals question mark 2 plus the square root of 2 times 2 minus 3. That is 1 equals question mark 2 plus the square root of 1. So 1 equals question mark 3, which is false. Therefore, the equation has no real solution. Summary. We isolated the root, squared both sides, expanded, collected terms into a quadratic, factored to get a candidate t equals 2, and finally rejected it as extraneous after checking the original equation. Here is the example we will solve. Step 1. Isolate a single radical on one side. Move the second square root to the right side. Step 2. Square both sides to remove the first square root. Remember to square the binomial on the right side completely. Combine like terms to simplify. Step 3. Subtract x from both sides to isolate the radical term. Step 4. Square both sides again to eliminate the remaining square root. Distribute on the right and move all terms to the left. Step 5. Factor the quadratic equation and solve for x. Step 6. Check both solutions in the original equation to avoid extraneous roots. Both solutions satisfy the equation. These are the final answers. Welcome! In this example, we will solve the equation, the cube root of 1 plus x plus the cube root of 1 minus x equals 2. We'll follow the classic algorithm exactly, step by step, and verify the result. Step 1. Cube both sides. We use the identity, open parenthesis, a plus b close parenthesis cubed equals a cubed plus b cubed plus 3, a b times the quantity of plus b. Here a is the cube root of 1 plus x, and b is the cube root of 1 minus x. Now we show the rule box. We apply the rule to cube both sides. Step 2. Expand the left side with the identity, then simplify carefully. First expansion. Combine 1 plus x and 1 minus x to get 2. Since the original sum equals 2, substitute that in. We obtain 2 plus 6 times the cube root of 1 minus x squared equals 8. Step 3. Isolate the cube root term. Subtract 2 from both sides, then divide by 6. Subtract 2. Divide both sides by 6 to get the cube root of 1 minus x squared equals 1. Step 4. Remove the cube root by cubing both sides. We'll recall the inverse rule. The cube of a cube root returns the radicand. Applying it gives 1 minus x squared equals 1. Step 5. Solve for x. Move terms to one side to get x squared equals 0, then take the square root. Bring terms together. Solve for x squared, then x equals 0. Quick check. Plug x equals 0 into the original equation. The cube root of 1 plus 0 plus the cube root of 1 minus 0 equals 1 plus 1, which is 2. Verified. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. Nenomatica, where mathematics meets YouTube excellence.